Thanks a lot for the introduction, Richard, and we move back to some musculoskeletal applications. I would like to talk today about strain measurements in bone. So it's somehow related also to the first talk of Andrew, where the challenge there is to catch strains in soft tissues, so large strains. In our case, actually, for musculoskeletal application, the big challenge is to catch small deformations. So I try to give a flavor of what we can do with our digital volume correlation approach. So in the talk, I will quickly go through some of the measurements that are currently available for strains in bones, and then talk about precision of digital volume correlation method, at least ours, and then I will just talk about two applications. So the main motivation of this method is to study the failure mechanism and the deformation in a complex material which is bone. So it's anisotropic, is not homogeneous, and it is a hierarchical material. So it's very important to study how bone deforms at all different dimensional levels. And considering the complexity of the structure, like in trabecular bone or in around cells, actually we need in details to get 3D, three-dimensional maps of deformations and strains in order to better understand the failure mechanism. Not only, but we can build many computational models. Of course, even in Insigneo, we can build many of them to study the failure mechanism in silico by starting from imaging modalities like clinical CTs, but also high-resolution micro-CTs for tissue-level applications. And in that case, it's fundamental to validate the computational output of the models, and in particular, the local outputs. So, for example, if we consider this tiny bit of trabecular bone tissue there, it's relatively easy to validate the output of this model for structural behavior, like stiffness and strength, but it's hard to measure, to understand how good is the model to measure the local displacements. And that's fundamental for multi-scale application, in particular if we want to understand how the cells which are laying on the surface of those tiny trabeculae are feeling the load and therefore can remodel the tissue. So strain measurements in bone can be done in different ways. So we can attach a sensor like a strain gauge that you have on the left-hand side, and that is a surface sensor. It's a few millimeters in size, and it's a very accurate measurement, but we need to attach it, we need to open up the tissue, and even for ex vivo applications, it's relatively invasive. In particular, if the bone we want to measure the deformation of is tiny, like a mouse bone. In the second case, in the middle, actually is digital image correlation. I will go very quickly through it, as Andrew already talked about it intensively. It's the same concept. So we can measure the strain in the sternal surface or in a portion of the sternal surface. In a 3D surface, we have a stereo method, and still we can do let's say monotonic tests, but at the same time, actually, as a limitation, we can't measure the internal strains and deformations. With the digital volume correlation methods, actually we can. On the other side, we need to combine the process with an imaging technique of the undeformed and deformed sample, as we will see. So usually we use CT scans, and we can do only stepwise loading. So we can't do monotonic tests, but we can do only time-lapsed measurements, and therefore we lose the ability of performing high velocity, high rate test. But on the other side, what we can get is a full 3D field of displacements and strains. So this is the standard approach. So we can take a sample, we place it inside a jig, and this jig can fit inside a micro-CT system. In our case, if we want to perform measurements at the tissue level, there is the trabecular bone samples of a few millimeters in size, and then we can perform a stepwise test, as reported on the right-hand side. So we can take an image of the sample in the undeformed or preloaded condition, like in the red dot, and then we can perform a second scan after we applied a certain loading condition. In this case, it's uniaxial compression, and perform a second scan at that loaded configuration. Then we can use an elastic registration algorithm to track the deformation. So applying directly to the acquired 3D images, we don't need speckle, we use the features of the object. And then this can get us a map of displacements that then can be differentiated into a map of strains. Now, I'm not going to, don't have the time to go into the details of the method. In Sheffield, we use as an elastic registration algorithm the Sheffield Image Registration Toolkit shared that was developed by Professor Rodhose and David Barber in the past for cardiovascular applications, and we adapted it for trying to catch the small deformations that we have in bone before failure. So the idea is that the algorithm provides the displacements in the nodes of this grid, which is overlapped to the two images, and then we assume in this case linear displacement within the cell of every grid. So if we use a nodal spacing, so the size of the grid, which is small, we get many measurement points, but then we may pay, as we will see in the next slide, and as Andrew showed for the DAC application, that something, and that something is that the precision of the technique is reduced. So since I arrived here in Sheffield 5 years ago, we did a lot of studies in understanding what is the precision, or the error in this case, in terms of strain measurements for different structures in function of the nodal spacing of the registration algorithm. And in reality, for example, we showed that if we use high-resolution images coming from synchrotron micro-CT scans with resolution in the order of 1.5 microns, we can get the errors which are much lower than the ones that you would get for standard micro-CT systems, or even from in vivo micro-CT systems. So, of course, the images then are affected by the noise that will affect the error in the measurement. So with these tables, actually with these graphs, we can, given an accepted error in our measurement, we can define the nodal spacing of our technique for the different applications. So in terms of first application, I would like to show you a collaboration that we did with the Flinders University in Adelaide in Australia, and Dr. Martelli and Dr. Perilli collected a beautiful cohort of images of the proximal femur that were scanned at high resolution with synchrotron at 30 microns, and they did a stepwise loading test where we acquired 6 images from the undeformed configuration until after failure, as you can see on the left-hand side. And this allows us to take the images, register all of them with the undeformed configuration, and use our digital volume correlation approach to map the deformation, so the applied displacements during that loading condition, and then to differentiate them in strains. So if we combine now this measure, so if we overlap, this is just a volumetric measurement of strain, but I report here only a longitudinal section of the proximal femur in one of the cases, from load step 1 to load step 4, which is just before failure. We can measure the heterogeneous distribution of strain, in this case minimum principal strain and maximum principal strains over the structure. And here I overlap it with the original structure of the femur. So we can start looking at where the strain localizes, both in compression and tension. We can overlap and put also their shear maps, and then start understanding why the failure in that why the femur in that particular configuration fails, and if the strain keeps localizing or keeps increasing where it first localized, even in the elastic regime. So another application for us, in particular for the modelers, is that we can use this information to validate the output of computational models, in particular what I will call micro-finite element models, which are finite element models generated directly from micro-CT images. So the concept is pretty similar. So from the deformed condition, we can then generate our finite element model with a large number of degrees of freedom, and then we can simulate the same loading that we applied in the jig, and then compare the output with our digital volume correlation methods. So this is the workflow that was defined together with Marco and one of his PhD students some years ago, where actually for trabecular bone, we can take the micro-CT image, we convert it into a 3D image, after proper segmentation, we just convert it into a micro-finite element model, we applied some boundary conditions, and then we get out the map of displacements, deformation, strains that we can get out from the model. This has been done in the past years. This validation has been done in the past years for trabecular bone, for vertebral bodies from the porcine, so where the structure actually is much more complicated, and also for the mouse tibia, because we have a number of preclinical applications where we want to make sure that our model are able to predict well even the local displacements under a certain loading. So this just the result is very busy. I don't want you to go into the details, of course. If you're interested in the details, please look at the papers which are referred to in the bottom. And basically, what I wanted to show you is that in reality, we have fairly good or to excellent correlations in case of displacement predictions for all the three types of bones that we analyzed. Of course, for the mouse tibia, you can see that we have some more variability in the measurements, some more higher errors, and then we are working on the modeling side to see if we can improve that prediction. And we have, let's say, the DVC allows us to have a benchmark that allows us to test different modeling approaches and make sure that we choose the best one in terms of local predictions of displacements and strains. So to conclude, I hope that I showed you how we can use the digital volume correlation approach to investigate and to measure heterogeneous deformations in very complex materials, even for small deformations. That we can, in any case, we need to accept a compromise between the spatial resolution of the measurement, so how detailed is the displacement field measured by the DVC, and the final precision of the method. So again, we need to find a compromise there. And then that this can be used also for validating the output of microfinite element models. Now this algorithm has been developed and translated into a web service that can be used by internal users of Insigneo right now, but also for external users soon. So keep looking at the Multisim web page if you are interested to use it, or let me know. I'd like to acknowledge, of course, the people involved in all of this, the collection of all this data, in particular my team, and the funding agency, of course. And maybe during the discussion, I'd like just to put there an advertisement slide for the Modellathon, which is a workshop that we are organizing in September for PhD students and postdocs who are interested in challenging themselves in a multi-scale modeling competition. So if you know anybody who's interested, or if you are interested, please let me know.
Thank you, Enrico. We've got time for a couple of questions.
Thanks, Enrico. You're taking a core, small core of the bone. How representative is that of the heterogeneity of the bone? You know, your deviation from when you get to the whole femur. To my mind, bone looks quite different on the edge than in the middle. How do you account for that?
Yeah. So first of all, we started from the core of trabecular bone because actually that was somehow the first application, but then we moved towards organ level measurements, let's say, but with higher resolution images like the whole proximal femur or the whole mouse tibia. Now, for your question, of course, making a mechanical testing without a small jig inside the microCT system, we have found that this is extremely, so it's very hard to control the uniaxial loading that we can apply to those cores. And that's, basically the trick there is that whenever we compare the output between the digital volume correlation and the microFI models, what we do, we use exactly part of the DVC output to set the boundary conditions for the microFI models. If we won't do it, of course, we will never be able to reach the nominal loading condition that we had before testing the sample within the jig. How representative is it for a typical loading scenario, to the typical loading condition within a bone? Well, I think that the only way is to test the whole bone, and where we can better control the external loading, and that's why we moved more towards organ level measurements.
Okay, if there's no further questions, we'll thank Enrico again.